possible. So today we're going to be describing common cooling methods. How do we keep things cold? Why do we keep things cold? We'll talk about chilled water and other particular features. And we're going to discuss thermal performance metrics. Okay, we have to do a little bit of maths today. Okay, it's not really horrible maths, but we do have to do a little bit of maths. I'm going to talk about things such as the airflow around data centers, temperature, humidity, and rack inlet temperatures. So we're going to talk about temperatures in different locations in our data centers. And we're going to outline methods of preventative maintenance. So how is the maintenance? How does that differ from our electrical maintenance? And what types of maintenance do we have to do for our HVAC and air conditioning systems? But we're going to start by getting everyone else to do some work. As you can see, I've been sat in the sun, caught the sun. Let's have a little chat amongst you. So we've got a discussion question here. Okay, so think about a time when you or someone you know basically had issues with cooling for either a computer, a device, or a room. Think about where and when it happened, what the problems were occurring, who did you contact for help, and how was the issue resolved? So let's open that one up into the live chat for you people to smash some details in. Give you some time to basically put your thoughts together. Think about those 4 key points. Patrick had a video card failure because the fan on a rig stopped working. Yes, video cards we know generate a hell of a lot of heat. They normally have massive cooling systems on, don't they? Well, I prepared earlier, that is a cooling system actually off a CPU cooling system. But you can see how big and chunky that is. Okay, so within PCs, yes, we do have large cooling fans. Within servers, we have them as well. I might show you some there. Annabelle says, have you heard of the underwater data center developed by Microsoft? Still testing. I knew there was a vicious rumor about it, but I didn't know they'd actually begun to put it into practice. I know there was some talk about doing something in one of the major lakes, or the locks as they call them up in Scotland. They were talking, literally, these are sealed boxes. So you put loads and loads of systems into it, you totally seal them off, you have a massive long cable coming out of it, and push them over the edge of the boat in the middle of a lock. Sinks to the bottom, because of course the lock water is really cool. Everything stays pretty cool, as long as you can keep that pesky stuff water out of it. The yellow light of death, where the soldering would melt from my PS3. Oh, we know that PS3s and the Microsoft Xbox basically had that as well. They had the ring of death on the Xbox, where they unfortunately used some slightly cheaper solder than they probably should have done, causing all sorts of problems with that. So yes, keeping things cool is really important there. Patrick basically solved his problems by, remember his issue with his heating, basically bought the loudest fan he could get after that. Better than putting it underwater, I guess, Patrick, isn't it? Gabriella used a stock fan in a PC. It was not enough to cool the CPU, but I tried AMD as a replacement. Good. Certainly these are solutions, aren't they? Screen goes black when it gets very hot. Yep. Laptops can be fairly susceptible. Has anyone here ever taken apart a PC that's 4 or 5 years old? Opened up the box? There's a question for you. I'm reading out some of these as well. Victor says, one time I was putting a PC together. It worked fine until I rebooted a couple of times. Checked the diagnostics tool and realized the fan RPM was 0. Yeah, that's not going to help, is it? Certainly if your fan is running 0, it's not good. There's a lot of different cables you need to connect to get things working properly inside PCs every now and again. And it could be the fan was actually running at 0. It could be the sensor connection wasn't actually established. In your space, Victor, I probably suggest it probably was the fan wasn't quite spinning, was it? Laptops overheated from Calvin. George basically says, had to repaste my HP on a laptop because it would overheat. By repaste, were you actually popping out the CPU? Or not quite popping out the CPU, but repasting as in using the thermal paste to recouple the cooling fan to it. And I said, what about putting a data center in the South Pole, North Pole, South Pole? They're a way to get to, aren't they? And you can imagine having fun with the diesel generators. If you lose power, who's going to deliver the diesel? It's hard enough to get it in Texas, and it's really sunny there. South Pole, who's going to drop that off? You can't just start melting the penguins, can you? Joshua overheats doing yard work in Texas. Yes. Well, in the UK, we've had a miracle day. We've had hot sunshine, beautiful stuff like that. I was shoveling gravel around for a friend today. We moved 2 tons of gravel through to his garden and spread it out where he wanted it. At least I hope it was where he wanted it. Stefan says, oh, that one's disappeared. No, solved with a hairdryer. There you go then. Yeah, you can basically reflow the soldering. They used to do that with the old Xbox. When you had a ring of death, there was a vicious rumor, and I may have tried this myself once. If you wrapped it in a towel and ran it, then it would super overheat and the solder would just sort itself out. Just dodgy solder, isn't it? Okay, so we all know there are particular areas where, yes, we have issues with heating. So it is important to keep things cool. So there's some fantastic examples in there. That's great. We know we can try to fix the problems ourselves, which is fantastic if you can. Great diagnostics from a lot of people finding solutions for some issues. Fan speeds running at 0, checking the diagnostics. Perfect stuff. Who do we contact to help? If we're not doing it ourselves, yes, we know we can contact a manufacturer. We can contact other people to give us a hand with that. And we have some resolutions in there. That's good answers. Thank you very much. Annabelle says, we've done it as well. Yes, basically putting the towel around the Xbox. Fantastic. Okay, so that's good. So let's have another thing. We've got 2 questions for you at the start. How cool of us is that? Imagine you're an IT manager preparing to set up a new data center. What considerations regarding cooling do you need to make? What types of cooling systems might you explore? What factors would you help determine the best cooling solution for factors? Let's take the top one. What considerations do you think we have regarding cooling do you think you need to make as an IT manager preparing a brand new data center? Let's have some answers in live chat. Loving the live chat today, guys. See quite a few of you typing in there. As an IT manager, what should I think about for cooling? Space, Greg says. Yes. What space do you have? How much space do you have to cool? Data payload and budget, Stephen says, or Stephen says. Yes, data payload and budget. We might need to redefine what you term as data payload because we're going to get into some technical stuff on that. But definitely data payload. Take it, that probably refers to a heat payload that you basically have in the center. Victor says, must be in my own mini North Pole. It's a good place to put it. Okay. Budget. Okay. Lots of things come down to money. It's all about that green stuff, isn't it? Budget, budget, budget. Keeping things cool for the cost. George says space, cost, and TDP levels. TDP level, George, do you want to define that for everyone? If you're using acronyms, I'm going to call you out and make you define it. Calvin says space. Nima says building layout. Yes, the building layout is very important. How far is your stuff from a suitable area to evacuate things? Redundancy and backup if some cooling solutions fails. That's from Patrick. Yes, very good. Weather. Yes, weather. Because of course we all know the cooling, the difference of cooling is basically the difference from our inside temperature that we're heating up to our outside temperature. And the greater the difference, the easier it is to cool. Difference is liquid nitrogen used. We don't use liquid nitrogen in HVACs. We use, well, we tend to use essentially the good old-fashioned liquid, which is known as water. And we use some other products that we'll come into in a minute and some details, which is our CFCs, aren't they? Yinka says building structure and design. Yes, again, building structure and designing space in the building is from Annabelle. Yet layout and topology, HVAC installations. Not all HVAC stuff is equal. So we've got to have some big considerations about those sort of things. So we kind of drifted into what type of cooling systems we might explore. We'll kind of skip over that because we come in that in some details. Oh, in fact, we've hit a lot of that. What factors would help determine the best cooling solution for your facility? So we know building design is going to affect how we basically design our cooling systems. More servers in a smaller space, liquid cooling. Definitely is a possibility, isn't it? So there's a lot of challenges basically as a data center, an IT manager, data center manager, in terms of getting your cooling systems right. In the old days, well, I say the old days, when data centers were young and growing up, we didn't have purpose-built buildings. There was never purpose-built buildings. I've walked around data centers that have literally been ex-warehouses. Someone's found a building, they found a warehouse, and they kind of gone, oh, we can turn this into a data center. So it is very simply, a tin roof, tin walls, etc., etc. Put racks on the concrete floor and building it in that sort of direction. So not everyone has the luxury of going, how should we design our building? What shape should it be? At what distance do we need to maintain between our HVAC system and the outside? You can't always pick and choose. So there are things that you have to work around. And yes, pipes, cables, and everything all over the place is going to be one of those considerations that you have. Great stuff. That is fantastic. Thank you very much. Okay, so let's pop on to the content and let's have a little look. Cooling systems, first lesson. First lesson goal is basically describe the common cooling methods. So let's have a little look at some of the cooling methods that we have. We have pumped refrigerant systems. We have chilled water systems. We have air-cooled and water-cooled. Chilled water systems, we now use a cycle of chilled water to cool air in the data centers. We're going to have a discussion about each in a little bit of details. Now, rather than kind of me reading across this, we will pop down and we will actually look at a couple of videos in a minute. Yes, we will do that in a second. I knew it was down there somewhere. But typical refrigerants that we tend to have. CFCs, oh, boo, yes, we drifted away from CFCs for some of our cooling stuff. They're highly effective, but phased out due to severe ozone layer depletions. You won't manage to buy a cooling system now with CFCs in it because no one likes the things. So we now use HCFCs, which is hydrochlorofluorocarbons. Wow, look at that. That's a mouthful and whole, isn't it? So these are a lot less harmful than CFCs, but they still contribute to ozone depletion, but they're being phased out under some international agreements. So now we're talking about HFCs, which is hydrofluorocarbons. Okay, these are ozone friendly alternative to CFCs and HCFCs. However, there's a high global warming potential, making them significant contributors to climate change. So we're either depleting the ozone or causing climate change. So we're doing one or the other. To be honest, we are generating an awful lot of heat in data centers. It's not massive in terms of the scale of the global warming that's going on, but it's still a contribution all round. So how we manage it is good. Now, to summarize, most of the cycles are pretty similar here. So we have something called an evaporative core, which is where warm air from the building or equipment is blown over an evaporated core. Okay, this is located indoors. So the refrigerant that is in there, whatever type it happens to be, absorbs the heat from the air, causing it to evaporate, hence the term evaporating core. So it goes from a liquid to a gas, and that itself absorbs energy, absorbs heat. Then we have the refrigeration, circulation, and compression. So this is where the evaporated refrigerant is drawn into the compressor, where it's pressurized, okay, by raising the temperature and pressurizing it for the next cooling stage. Then we have the condensing coil, where pressurized refrigeration is pumped through the condensing coil, where it releases heat. So as you squish it and pump it through this, it releases the heat outdoors. So we've got essentially two things. We've got a unit that sits inside the building, and we've got a unit that sits outside the building. Okay, and obviously the inside one is sucking the heat in by evaporating the coolant, and the outside one is letting the heat out by compressing it. Now we've got some good videos here to basically explain how that happens. So I'm going to check my share. And we're going to let you watch some of those, and then we're going to come back to some of these items, okay? So the first one is the refrigerant cycle.
Welcome to the MEP Academy.
Everyone can hear sound? Thumbs up for sound. Thank you very much, Victor.
We're going to cover the refrigeration cycle and the four major components, including the basics of heat transfer. We'll quickly go over the refrigeration cycle, and then we'll cover the individual components and the physics behind it later. But real quickly, you have four components. The number one is the compressor. That's what is the heart of the system. It takes low pressure gas and pumps it up to a higher temperature and higher pressure gas. The gas flows along this line over to the condenser, where the gas is condensed into liquid. It gives up its heat to the outside air. This is where you'll find a condenser outdoors. This is an air-cooled condenser. It's cooled by the air, so the gas condenses into a liquid. So you don't see these dots anymore. This gas represents gas. So this is liquid now going through the tubes. And you got to have liquid when you get to your metering device. So this controls the high pressure and the low pressure liquid. So you got high pressure liquid coming in, low pressure liquid coming out. Now this liquid is going to boil. It's going to take the heat from the room and boil. So the heat will make the refrigerant boil and turn back into a gas. And then the gas will make its way back to the compressor, and that's one complete cycle. High pressure gas to high pressure liquid to low pressure liquid to low pressure gas. That's the complete cycle. Now heat flow. Heat flows from warmer medium to cooler medium. It always flows in one direction, from the warmer to the colder. To understand the compressor, you'll need to understand the relationship between temperature and pressure. It's very simple, as they act in the same direction in the refrigeration cycle. If you increase the pressure, then the temperature also increases. That's what the compressor does. It raises the pressure of the vapor from the low side to the high side. The same is true if you decrease the pressure, the temperature also decreases. Pressure and temperature move in the same direction like a one-way highway sign. In the refrigerant cycle, we have the high side and the low side. Okay, one more simple explanation about physics before we move on, and that is the phases of refrigerant. So you're familiar with water. So water has three phases. You have the solid phase, which is ice. You have the liquid phase, which is water. And you have the gas phase, which is vapor. So in the refrigeration cycle, you only have two of these phases. That is liquid and gas. We never get to solid. If you get to solid, you got a problem. So you only have liquid and gas in the refrigeration cycle. And this refrigeration cycle is a continuous changing of the state of the refrigerant from gas to liquid and then liquid back to gas over and over again in the process while moving heat around. There's basically only four conditions you'll find in the refrigeration cycle. You're either going to have high pressure gas, high pressure liquid, low pressure liquid, or low pressure gas. Now, what you will find besides these four is that as the liquid is evaporating or condensing, you'll have a mixture of both liquid and gas. But by the time you get to the compressor, it has to be all gas. The compressor only deals with gas. And by the time you get to the metering device, you should be all high pressure liquid. Subscribe for additional videos. We will be covering mechanical.
So any thoughts on what you basically heard there? So we know the relationships. Here's a question for you all. Well, I can see Calvin typing, very interesting. We spoke about a compressor and what the compressor does. Where is your nearest compressor to you right now? Does anyone know where the nearest compressor is? You've got an AC unit, Greg, obviously living in a hot country. AC unit. I'm by a vending machine. Yes, vending machines need to keep things cool. They have a compressor unit. Greg, fridge. I was hoping everyone was going to say fridge, refrigerator. A lot of you have got AC units. Crikey. I dream about living in a country warm enough to need an AC unit. Car outside. Yes, you have a compressor unit in your car, basically, that runs your air conditioning, don't you? Yes, so certainly that compressor unit, you can hear it kick on. It's a motor. It's simple as that. So it's basically squishing things up. So you can hear when your fridge basically kicks in every now and again. That is it driving that motor, pushing stuff around and basically helping to cool your fridge. Calvin's in the Amazon break room. Okay. Okay, so any questions? We know there's a relationship between pressure and temperature. Okay, we know full well when things get squished. Well, I don't know full well. We know when things get squashed, they become hotter. And this isn't just by friction. It's basically about cramming those excited molecules into a tighter space, which means they bump into each other more often and therefore create some more heat. A good example of excessive pressure and heat, diamonds. How are diamonds created? Diamonds are really created by being underground. You've got carbon, pure carbon for the best diamonds that gets squashed by all the massive pressure that's basically there underneath the ground. That then causes an awful lot of heat as well. And that heat and that pressure basically then makes the carbon form into a girl's best friend, our friendly diamonds, don't they? Thank you very much, Omar, Robert. Yeah, pressure and heat, Kenneth. Fantastic. But also we know when we have less pressure, it gets colder, doesn't it? So here's a good example of us getting less pressure and getting colder and colder. Can anyone think of one of those? Something that we all experience. Elevation. Robert, well done. God, there's a bonus point for anyone that can tell me how many degrees. Well, that's a horrible question if people don't deal with degrees C. How many degrees C do you change for 100 feet in elevation? Or is it 1,000 feet in elevation? Probably 1,000 feet. 32. Yeah, not quite 32. But certainly when we go up, we know full well the higher we go, the less pressure we have, the colder it is. Okay, this isn't just the fact that we're further away from everything, it is actually colder up there. Okay, so we've got a question there from Kadir. How do pumped refrigeration systems differ from chilled water systems in terms of efficiency and maintenance requirements? Very good question. I'm not going to dive straight into that one because we've got another video that hopefully will explain it for you, or at least give us some further insight. And it does basically come for terms of mid-size and large data centers. Right, so what we got there was very simply an air-flowed one. So let's have a look at the water chillers.
We're going to look at the difference between an air-cooled chiller and a water-cooled chiller. We're going to look at the refrigerant circuit, how heat is moved around, how heat is rejected, and where you might locate an air-cooled chiller as opposed to a water-cooled chiller. The main purpose of the chiller, of course, is to remove heat from the occupied space. Heat comes in the way of people. People generate heat based on the activity level. Whether they're sitting, it's less than they're doing exercise. If they're doing exercise, it's going to be generating more heat. And then you got lights. The different kinds of lights produce different amount of heat. You got plug loads, which is your anything that's plugged into the outlets like computers, any machinery. And then you have your solar load, which can be shining through the windows, or the conductance of the temperature difference between the outdoors and the indoors, and the resistance of that wall will give you a certain amount of heat gain. That's the heat we want to remove and bring that to the chiller so that we can cool down the space. I'm going to show you how a refrigerant circuit for a water-cooled chiller and an air-cooled chiller is somewhat similar to your home air conditioner. Here's a layout of your typical refrigerant circuit. And the four components that you'll find in just about every refrigeration system is you have the evaporator coil. And this one, it's air-cooled. You see the fan. And on the other side, you have the condenser coil, and it's air-cooled, as you see the fan blowing over the coil. And then you have the compressor, which moves the refrigerant around the system. And then you have the expansion valve or metering device that controls the amount of refrigerant that goes from the high side here in red to the low side in blue based on the demand required. Now, if we want to make this into an air-cooled chiller, then we need to get rid of the fan and bring in a heat exchanger, a shell and tube heat exchanger, and then we'll pipe water in and out of it, which will be cooled by the refrigerant. So now the refrigerant, instead of having air blow over the cold coil and blown into your room, now the refrigerant will cool water, and water will be taken to an air handler, which will then blow over a chilled water coil and cool the room. Now, this leaves us with the condenser side, which is air-cooled still. We still have a fan blowing the heat to the outside of the building. Now, if we want to make this a water-cooled chiller, we need to get rid of the fan and also bring in another shell and tube heat exchanger and piped water in and out of it. So now instead of the heat being thrown outdoors with a fan, now we're going to pipe in water, transfer the heat from the refrigerant to the water, and take that water and the heat with it to the cooling tower, where we'll reject the heat and bring back that cooler water and start the whole cycle over again. So all we've done here is gotten rid of the fans that were doing the work of the heat transferring, and now we're using heat exchangers. They exchange the heat from the refrigerant to the water, or from the water to the refrigerant. The refrigerant and the water never mix. In this case, the refrigerant is going on the outside of the tubes, and the water is going through the tubes. So remember, heat comes from people, plug loads, which is your computers or anything plugged into the wall or any equipment generating heat, lighting, and any solar. If you had windows here and the solar was coming through, or you have the outside air, heat on the other side of the wall coming through the wall through conductance, you have that heat generated in this space and you want to remove that. That's represented by this heat molecule here, and what will happen is we'll take that heat through the return air duct into the air handler and pass that heat into the chilled water system. And from there we take it into the chiller, and we'll continue on the next frame. Okay, now the heat has arrived from the chilled water. We've picked it up from the room, we brought it to the chiller, and that heat is going to cause the refrigerant, liquid refrigerant on the low side in the evaporator to evaporate, and it absorbs the heat, and then that heat is taken through the compressor and gets compressed to a high side vapor refrigerant, which passes it to the condenser and into the condenser water and into the tower and then out of the tower, and that's how we get rid of the heat from the building, from the chilled water circuit, through the refrigerant circuit in the chiller, to the condenser water circuit, and out of the building. Now, of course, a water-cooled chiller is more sophisticated than your residential package unit or split system that you find at home, but they have the same four components: the evaporator, condenser, compressor, and expansion valve. As you see here, this water-cooled chiller has all four of those. And to identify the components, you can see that the evaporator is insulated. Oftentimes, the majority of the times, you're going to find insulation on the evaporator. That's to prevent heat from getting into the evaporator. And the condenser will be uninsulated. And then your compressor is going to be sitting a lot of times on top of the evaporator, not always, but in this case it is. And there's an elbow going into, from the compressor, into the top of the evaporator. And then at the bottom there, you'll see the expansion valve. Okay, now if we look at an air-cooled chiller, we can identify the same components. You can see your compressor, there's two of them, one here, it's got two circuits, and one here. And then your evaporator, you can see the barrel in the back there, that's the evaporator. And here's the suction line coming off the compressor, so it's sucking from the evaporator into the compressor, through the hot gas discharge, into the air-cooled condenser. Now here's the coils for the condenser, and here's the fans on the top. And turning this, we can see that we're going to have some expansion valves over here before we go into the evaporator. So it's a dual circuit, meaning we got two separate circuits. One circuit here with his compressor and another circuit over here. And here's an expansion valve here, an expansion valve here for the separate circuits. So often you'll have a dual circuit to control capacity. And here's the coils. These are copper coils, most likely, aluminum fins. And the refrigerant runs through there. and then the air is sucked from the outdoors over the coil and blown the heat straight up and out. And this is located outdoors, but this is your air-cooled chiller. All right, so if we look at this, number one here is the refrigerant circuit. That's within the chiller. The chiller has the four main components: the expansion valve, the condenser, which is a heat exchanger, shell and tube. It's got a shell and it's got the tubes. 3, the compressor, and the fourth component, major component, is the evaporator, which is similar to the condenser. It's a shell and tube heat exchanger. Now the process begins by this low side liquid refrigerant coming in at a cooler temperature than this chilled water. So the heat is given to the refrigerant, causing it to go from a liquid to a vapor, causing it to evaporate. And that evaporated refrigerant inside this chiller goes into the suction side of the compressor, which compresses the refrigerant to a higher temperature, higher pressure vapor, gas, which then travels to the condenser, where the vapor is to be condensed, meaning it's going to turn back into a liquid by giving up its heat to the condenser water coming through the shell and tube heat exchanger. Now the refrigerant and the water never touch. They're separated by these tubes. The refrigerant then condenses, going back to a liquid, high side liquid, high pressure liquid, where it comes to this metering device, this expansion device, which meters the amount of refrigerant onto the low side based on the demand of the chiller. So it goes from high to low pressure liquid through this expansion valve. Okay, so the first thing we've got to do is give each floor an air handler, a chilled water air handler, which we're going to provide chilled water to. There can be one or more of these per floor, or there can be several on the roof. Somewhere you can put these air handlers. They can be indoors or outdoors. You can get waterproofed ones, weatherproof for outdoors. Now you got an air-cooled chiller. This has to be outdoors somewhere. So either on the ground floor, it can be on the low roof, it can be on the upper roof, but then you have to pipe it with chilled water to each one of those air handlers. Wherever you put them, you got to get the pipe there from that air-cooled chiller. So if you put that air-cooled chiller on the roof, then you got to pipe it from the roof. The good thing about putting it on the roof possibly is maybe it's out of sight if you don't have floor area or area on the ground level. Now, if you go to a water-cooled, you got the same air handlers, one on each floor, multiple on each floor, but then you have a water-cooled chiller. Now, this is not made for outdoors. The majority of these are indoors. You can get them made for outdoors, but that's very rare. The majority of the times, these are indoors. They're in the basement, they're on the first floor, can be on the roof. Wherever you put it, you still need to pump that water from the evaporator to the air handlers. But with water-cooled chillers, you got one more piece of equipment to worry about, and that is the cooling tower. So the cooling tower can be put on the ground level, or it can be put on the roof. But once again, you're going to have to pipe from the condenser side of the water-cooled chiller up to wherever you put that cooling tower. So you got to think about the routing of the piping of the condenser water. Now the condenser water majority of the time is not insulated, so you don't have that expense. But you got to remember, those cooling towers are big and heavy. The more tonnage you got, the more cells there are. These things can weigh 30,000 pounds more. So you got to have structural reinforcement if you're going to put that on the roof. So you can put it on the roof or you can put it on ground level. But those are some of the things to think about. If you like that video, please give it a thumbs up and subscribe to our channel. Thank you.
David, you're on mute. Sorry.
I've got a t-shirt upstairs that says you're on mute. I'm not wearing it today, possibly I should have done. That was great. Do we have any questions about that video and some of the items that were covered in it? We can see there are different types and different solutions, and they all have different attributes that make them either good or bad for items. Okay, some of the pros and cons are worth basically looking at some details. Kadir, you're preempting the majority of my work today. Thank you very much. I love that. Good work. I should hire you. Okay, so air-cooled chillers. Pros, they're simple installation. No need for a water supply. Okay, pumping water around is obviously good fun, isn't it? There's low initial cost for it. It requires less maintenance. Some of the bad things on it: higher operational costs due to energy consumption. Okay, depends on outdoor ambient temperature a lot more. May require additional space for installation. Okay, they are typically put in residential buildings and small commercial spaces. Water-cooled chillers. Okay, they are highly efficient, especially in large spaces. Operations, they operate quietly. We are pumping water around, of course. They have a longer lifespan on some of the equipment. Some of the cons on it: it requires access to a water supply and treatment system. They are more complex for some of the installations. A lot of that is basically because you are simply dealing with water, isn't it? And the initial cost is higher than the air cooling system. These tend to be the ones that are used for large commercial buildings and industry facilities. Okay, so potentially these water-cooled systems, water-cooled chillers, are the types of systems you might be encountering in data centers. Now, there is also a pumped refrigeration system. High energy costs. Okay, we don't want to spend lots of money. It's high energy costs. They are compact designs, suitable for smaller spaces that you need to keep really cool. Individual temperature control in different zones is very achievable with the pumped refrigeration systems. Some of the cons on that is that they have a higher initial cost compared to other systems. So installing them is quite expensive. And it does depend on the refrigerant type available. Okay, now we are getting more and more restricted over which refrigeration type we should be using. The price is basically varying in there. So they are less suitable for large scale applications, but really good for smaller scale applications where you want to maintain the control on the temperature in different locations. These are great for your residential air conditioning and small commercial buildings. So those are sort of the pros and cons in there. Does anyone have any questions or anything they'd like to ask around those systems? Kadir is asking, what strategies can data center operators use to mitigate the operational and environmental impact of high water consumption in water-cooled chilled systems, particularly in regions where water resources are high or highly regulated? Again, you know, you can have condensers that basically redo your water system, so bring your water back down. These are the cooling towers. Okay, because when you are cooling, you are eventually evaporating water in some of these systems. That evaporated water then basically means you've got to reclaim that in some way. So you've got to do some reclamation. And again, that is to say, there isn't sort of a one size fits all. It's very much a case that depending on the area you're in, if it's a high ambient temperature outside, you may choose a slightly different solution to someone that has a low ambient temperature outside, or indeed has put their data center underwater in big boxes. Good, that's fantastic. Okay, so there's the pre-diagrams we won't go into. You can refer to those as you like. But you can see here we have water pumps. We can compare our water going around the systems when we're dealing with the water-cooled chillers. In comparison with the other systems, the air-cooled chillers, where we are simply blowing air around. Good. I'm going to move on to the next block then, if everyone's good with that. A couple of pretty good videos there. So cooling methods and techniques. We're going to look at things such as the hot and cold aisles. What are those? Rack placements, where we put our racks, blanking plates, free cooling. Free cooling, what does that involve? Things being cold outside. Containment and cable organizations. You wouldn't believe it. All these sort of things basically evolve around the efficiency of our cooling systems, which is what we want. Remember, the more money that we're spending on cooling our system, remember we spoke about our electricity usage. So the more money we're spending on the electricity to cool our system, the less money we basically have for our IT systems, and that unbalances that beautiful figure we were talking with yesterday. So cold aisle. Who's been around a data center before? Show of hands, who's been around a data center? Good ear, good. That's smashing. Daniel's seen one. Catherine showed me two eyes. I assume that's a yes. I see a couple of you typing. Let's see what's coming up. As I say, we've got plenty of time today. Neymar did security at one. So there you go. So we've got a few people that have been around data centers. One thing you will notice about data centers is we say, yes, there's loads and loads of heat produced in data centers. But every time you will see a data center knock technician, they always come to work with a jumper or a jacket. And the reason for that is because we have cold aisles. Cold aisles is literally where all the cool air is being pumped into the systems. So it normally comes up through perforated floor. So you have a perforated floor grid in the middle of the aisle, and you have servers on the left, servers on the right, well, racks on the left, racks on the right, because it's not just servers. And all that cold air that we've now produced, that we're basically going to chill everything out with, gets blown up from underneath you. And if you are stood in a cold aisle, yes, you are freezing. It's not totally freezing, but it is pretty damn cold. There was an event at IMART, the data center that I used to work at. We have a massive security for a lot of our data centers. We have sealed cold aisles because that's the way they should be done to make them more efficient. But with sealed cold aisles, you have doors at either end. You have a polystyrene roof. Okay, you have racks either side. We had one poor guy, unfortunately, managed to get himself locked in a cold aisle. He spent 3 hours freezing himself senseless in a cold aisle. It's not quite like, you know, the movie stuff where they lock someone in a big freezer, a meat freezer or something like that. But my God, he felt very, very poor when we got him out of there. Jumper or jacket, PPE. It's not quite PPE. It's definite equipment that you need for a cold aisle, and we need it for the servers. Hot aisles. Okay, so we have hot aisles, which is great. So as soon as you walk out of a cold aisle, you end up in a hot aisle. So you're taking your jumper off. So make sure it's got a zip or something like that. Can be like that. Basically, the airflow shows the airflow model here. Cold aisle you have at one particular location where the cold air is coming in to the front, and then it blows it out the back, which basically makes a hot aisle. So all that hot air that is generated by the servers is getting blown out the back. What does it get blown out the back by? Let me show you. Oh, I'm going to turn it off. So that is a HP server, a DL380, I think it is, or a 360. I can't remember which one it is. Okay, it's a 2U server. This is what is causing a lot of our heat. Okay, we have processors with air conditioning system, processors with their cooling systems basically on them. We have disk drives at the front that are producing heat. Okay, this is what creates the heat. The whole idea of this system is that air comes in the front end, gets blown backwards, and comes out of the vents at the back. Okay, server systems will have numerous fans. These are hot plug and play fans that are literally designed very simply to blow the air from the front to the back. Okay, HP systems tend to have this look. This is a plastic case. Okay, and the idea of this plastic case is that it dedicates these two fans to blow air directly across the processors. The other two is just blowing air from the other locations through the other systems. Okay, this allows us to change the speed on the fans to keep the processor cool. So if you're doing a lot of hard work on this system, processors get warmed up. These two fans increase in speed, blowing more air across the processor. This basically stops the air. This stops the air getting muddled as it gets blown through the system, so it doesn't go round in circles. Okay, this is why we have a cold side where the air comes in and a hot side out the back. So therefore we have a cold and a hot aisle. So all servers work like that as well. So all servers will have systems similar to that. But it's not just servers. Your racks will basically have things such as your storage devices. It will also have switches and firewalls and everything like that. Now, a general rack basically is 42 U's high, so you can mount 42 individual use systems. Very rarely you ever do that. But within that rack system, you then make sure that your devices are faced the right way round. Who's heard the term TOR, top of rack switch? Yeah, thank you for sticking a hand up. We learned about that recently from Patrick. Yep, went over that. Veterans. Okay, so top of rack switches. Very important. Top of rack switches are normally placed at the top. And they are normally placed at the front. Is there any reason we can't place it at the back of the rack? Anyone think of a reason we can't place them at the back of the rack? Simply they will be turned around and face the other way, plugged in. Too hot. Walls. Yeah, walls and other things like that. Heat exhaust. The simple reason they tend to be placed at the front is because 99%, in fact, all manufacturers basically design their switches so they blow air from the front to the back. You can buy switches and other devices that are designed to be mounted at the back of a rack. Okay, and they suck air from the back and blow it out the front. But don't get them the wrong way around, because if you put them the wrong way around, you are messing up the airflow system. You don't want to be blowing hot air back into the systems you are trying to cool. Okay, so make sure you have them the right way around. So pay attention on that. Normally, everything is designed simply to blow from front to back. It's as simple as that. But there are switches and top of rack switches certainly that are designed to do the other way round. Patrick, not so much accessibility. Most data center racks, basically, you can get in the front and the back without any problems. But a good answer, though. I can see Patrick typing this, so let's see what he's come up with. Patrick basically asks, is it common for internal fans for these components to be modifiable in terms of airflow direction? No, fans tend to be one direction only. If you will tend to purchase one that says it blows air the other way. So you'll actually specifically request that from the manufacturer. Normally on your servers, when you're plugging fans in, they will only slot in one way. I showed you the lifting out of a replaceable fan unit. That fan unit will only slot in one way. So it's very difficult to get them facing the wrong way and blowing things in the wrong direction. Okay, so we talked about airflow. It's all about airflow, because the only thing we are cooling our systems with is air, essentially, in those racks. So a proper rack layout will optimize the airflow. Okay, it's a key factor in it. So if we look at these particular systems, this is an open racked system in that image, because there's no cover over the top of that cool section. Okay, you can see it's just a big warehouse, essentially. Everything in the front there is sucking the cool air that's down that big aisle, okay? You can have closed cabinets. Closed cabinet ones are the types that basically do have a front and a rear, and everything should be closed. So it is very important to get that correct. Now, when you walk down an aisle, you'll kind of wander down, you will look left and right. You'll see servers basically in there. You'll see switches, you'll see data systems in there as well as firewalls. One thing you will also notice in there is things called blanking panels. And everyone looks at those and goes, oh, what's the point of those blanking panels? A blanking panel literally sits in the space where you would normally put a server. They're normally one use, so they're single use, so you will have multiple blanking panels. When you want to install a server, you take out this piece of plastic, put it on the floor, don't throw it away, put it on the floor, and then you will slide another server, mount another server in there. The reason that's done is because we don't want the air to move around inside that rack unless we are pushing it. So unless it is doing useful stuff such as cooling our servers, we don't want it to move anywhere. Most servers, well, all servers and all switches are closed boxes. So it's important that we get the air from the front only through the system. We don't want to send cold air through to the hot aisle without cooling anything down. And that's why we have blanking plates. They do have a massive effect on the airflow in the systems. That's a beautiful looking data center, isn't it? None of them look that tidy, to be honest with you, but that's a beautiful looking one, isn't it? Any questions about blanking plates? And then, as we all mentioned earlier on, free cooling. We'd love free cooling. Free cooling basically is about putting your data center into the right place. Oh, Kadir's asked a question. What role do blanking panels play in directing flow within server racks? And how might improper use of placement of these panels affect cooling performance? Okay. What's the best way to put this? Greg basically comes in. They block the air moving through. What's a good example? I'm trying to think of a good example. Oh, okay. If you imagine a harmonica, everyone knows what a harmonica looks like. You blow a harmonica, you blow the air through it, and that gets you the sound. So imagine the sound is basically the cooling. So if you're blowing a harmonica and you're only blowing through the harmonica, all that cooling is going through one thing. Now, if you take the harmonica away from you and you've got no blanking plates, essentially, controlling that air going just to the harmonica, air will blow elsewhere. And that air is lost. So that cooling is lost. It's not making noise through my harmonica. It's just blowing over the top. I think that might be a good example, Kadir. Does that make sense? Because it controls the airflow. Greg says they block it. Perfect analogy. I like that. Great. Remember, it's all about controlling where the air flows and where the heat is taken from. Good. Kind of wasting air if you don't have a blanking plate. Exactly that. You're not focusing it down the channels that need to be cooled. You're just letting it go from the cold aisle to the hot aisle without doing anything. Okay, so we said free cooling. We had some fantastic chats earlier on about geographical locations. Why don't we put them all in the Arctic or the Antarctic? yes, you can put them in milder climates, you're going to get better success. Because remember, it's all about the difference between the two temperatures. Again, it's all about making sure that your operational temperature, if you can run your equipment at the data center at a higher temperature, then free cooling might be a good choice because you have to spend even less basically on it. So if you can keep your data center in the right location where your operating temperatures are within scope, then you could basically say, well, I don't actually need any air conditioning. Oh, horrible thought for me. No air conditioning. So that's the important thing. So containment. Containment basically consists of cooling containment systems, basically enclosing the rows, enclosing the racks of the servers to make sure that that air is going to the right locations. So cold aisles are normally totally enclosed. So you kind of have a grid, plastic panels, you have all the air conditioning comes up from the bottom and it hits simply a locked, closed off corridor where the air has one choice, and that is to go through a device to the hot aisle. And that is your maximum efficiency. So it comes in cold. The only way out is through one of those devices to keep it cool. Hot aisle containment. Yes, we do not want any of our hot aisle air to go elsewhere. We want to basically make sure that stays where it's supposed to go. It goes to our refrigeration system that is then basically going to deal with taking all that heat out. That's where it should be going. Any waste of that hot air or any hot air that strays elsewhere is going to influence other systems. It may not influence the aisle that we're in, the cold aisle, may not be able to get in there, but it'll influence other areas of the building. We want to basically take that hot stuff and we want to stick it straight out and get it compressed and cooled and sorted out. So if you improve your airflow, you can expect up to 30% increase in cooling efficiency. Don't mix your air systems. Keep cold, cold, hot, hot, 30% increase. Man, who would want a 30% payment increase? That's a massive amount of money. So you get a higher return essentially on the temperature for air conditioners, improve their efficiency, and you get an ability to control the aisle temperature. Controlling the aisle temperature is critical because if my aisle temperature is hot, then my fans in my servers have to run harder to keep the TPUs cool. So if my fans are running harder, I'm burning more electricity to run those fans. We all know in our PCs, if our PC fan is basically running really high, it's because it's hot. Okay, so that's our fan turns up to try and keep the system cool. If you've got 200 servers and all of a sudden your temperature goes up 1 or 2 degrees, and they all of a sudden are drawing a few more amps, or watts, I should probably have said, of power through it, then you are spending more money because you're inefficiently cooling those systems. Drop that a couple of degrees, they fall within that parameter, and then you're burning less electricity. Here is a contained aisle. Yeah, there you go. Joshua, perfect timing. Here is your cold aisle. We are literally talking about aisles. A walking channel with racks on the left and the right. You can see the perforated floor at the bottom. That's where the cold air comes up. Your server cabinets are on the left and the right hand side. You've got a perspex lid. Air comes up through the bottom. The only choice it has is to basically go out. Doors at the end. Those are the fun ones that you should never lock behind you. Will never get locked. Does everyone understand? Let's have a thumbs up. Does everyone understand the concept of the cold aisle and why this is so important? Stephen, Kadir, Joshua. Yep, fantastic. Mindy. That's the first time I've name checked you, Mindy, I believe. Good. Now, not only do blanking plates pay importance, we will say this again and again throughout this. Airflow, airflow, airflow. Anything you can think of that gets in the way of the airflow and stops the airflow or fails to direct the airflow is a problem. Cable organizations. Who's been in a server room, old-fashioned server rooms, where the cables initially, when it's first installed, are beautifully tied up at the side. They're lovely. They come down little cable management systems. 6 months later, they come to the same room. It's like a spaghetti junction. Those cables, I don't know how they do it. They just manage to do it themselves. They get all over the chip shop. Okay, so it's really important. You can imagine a nice tight bundle down the left-hand side of the cabinet doesn't get in the way of the air. A whole load of spaghetti junction down the middle acts very much like a fence. It stops the air blowing through. So you've got to have cable management systems that tidy those systems away. Here's a nice, neat little one there, basically all pulled up. That's a fiber optic channels, I believe they are. They'll all be pulled down into the cable management system, which is this black section, and then be pulled off to the left or to the right. So they're not dangled down. Here's a quick discussion question. And I think after the discussion question, we'll probably have a 15-minute break. At the various data center cooling methods we've learned about, which approach do you think is the most impactful for efficient cooling IT equipment? What factors make the method so important? What best practice would you emphasize to maximize? And after this, we'll take a 15-minute break. Water cooling from Stefan. Omar says water cooled. Why is water cooled more efficient than air cooled? Good question for you there. I'm throwing that one out to you all. Feels like best control of your airflows, King Patrick. So true. You can make a massive efficiency benefit if you have your airflow sorted out. Containment from Bertrand. Yes, exactly. Kadir, I believe the answer is containment. Well, fantastic. We're getting there, aren't we? Lowers the temperature further. Here's a good example. In your area, in the area that you're in at the moment, without putting a hand on a fridge or talking about a fridge or anything that is falsely refrigerated in any way, what's the coldest item in your area? And this will help explain why water is more efficient than Daniel Hart. Good to see some comedians out there. Kadir asks, whether hot aisle or cold aisle is often the most impactful method for efficiently cooling IT equipment by preventing hot and cold air from mixing. Yes, definitely, you've got to prevent that from mixing. Containment system allows the cooling infrastructure to target the service. Man, you could have written some of this. Kadir, that's exactly it. Okay, it contains the system, prevents the hot and cold air from mixing, and therefore targets the inlets, and it keeps them cool. Water cooling system, sink, water, heart. Surprised no one's mentioned anything metal. Okay, let's have this example. Yeah, we've got a. This is something I remember from when I was young. This is something the teacher taught me, and I might as well pass it on. Okay, here's two items. Which one of these two is the coldest? Nice wooden pencil is the coldest. Or this what happens to be it's a metal PSU. Metallic plate we've got. Metal from Joshua Yinka, basically says metallic plate. The pencil isn't insulated. Very well. Daniel, you probably could have sat in the same physics lesson as me. Metallic plate. Trick question. It's the pencil. It's not a trick question, Gabrielle. They've both been sat next to me on my desk. So it is a little bit of a trick question. I see a couple of you are actually still typing answers, so great question. Is the metal separator between the pencil and eraser? Robert, Kadir. Well, it's a trick question, so if we happen to set them on fire, which two will generate more heat? Okay, the granite and the pencil. Okay, the actual answer is, the big answer on this is the temperature of both is exactly the same. Okay, they are both at room temperature. They're the same temperature as the desk, as a piece of paper. They are both at room temperature. The metal feels colder because it's a better conductor of heat. So my body is warmer than the room temperature. This is at room temperature. When I put my hand on the metal will conduct that heat away. Remember we saw that video where we talk about heat going from hot, my hand, to cold. This isn't actually cold, this is just cooler than me, okay? So the metal conducts it away faster. Whereas the pencil is wood, it's a very poor conductor, and therefore when I pick it up, less heat is taken from my hand through the pencil. So they're both exactly the same temperature. This is what makes water better at removing the heat, because it's a better conductor than air. Air's a rubbish conductor, let's be honest. It's a rubbish conductor of heat. That's why we have it in our double glazed units. That's what keeps us warm in our duvets, is the air that gets trapped, because it is a poor conductor. There, good. Glad we managed to get that one. Okay, so that's fantastic. So we've had a good bit. We're going to have a 15-minute break where you can grab a coffee. Well, I've heard you wanted a chance to basically pop out, get another coffee, quick comfort break. Let's see who is ready to carry on. We have additional consideration slide. Fastest thumbs up to let me know that you can see that slide, and then we'll kick back into this. Daniel fastest, thank you very much. Patrick, Sunil, George, Stacey, Mindy. Right, okay, let's get on. Okay, so there are additional considerations to basically be made. It's called HVAC for a reason. We need to consider humidity. Okay, so humidity in a data center can be between 20 and 80%. Okay, lower humidity is probably better. We like drier systems. It's always the way to do. We also need to consider things such as the dew point. So the temperature where water vapor basically turns into liquid must be closely monitored. We need to avoid water forming on our equipment. We love water for cooling. We hate water for basically getting in our electrics. Most data centers run between 64 and 80 Fahrenheit. So cooling is very expensive. So really we need to find the right temperature and the right way to basically go about that. There's a quick section review. If we can fill out the 3 questions on the section reviews before we drop into, if you have any questions on the section review, please do. I will give you 2 minutes, we say a couple of minutes basically to get through that. Yeah, a couple of you typing a few questions there. Or typing anyway. Section review at the end of cooling methods. So let's see it here. Have you found that, Joshua? These are really for you to fill out, aren't they, within Codio? Okay, well, let's not over worry about that. That's what's shown on your page, probably is. Let's not worry massively about that then. Let's drop into, how do I access the questions? I put them in live chat. I thought they're supposed to be in Codio, but let's carry on without doing those for today. I'll have a look at that in the future. Okay, so let's talk a bit about heat loads. The heat load basically refers to the amount of energy that's produced by your systems. Now, we can break this down into individual systems. So we can kind of look at a data center and think, well, what equipment produces heat in our data center? Well, we've got servers, we've got networking devices, and then we've got other IT devices. So the unit of measurements that we basically look at are BTUs, which is British Thermal Unit. So we bring you something, if nothing else. So a British Thermal Unit, it's basically the amount of heat to raise the temperature of 1 pound, look at that old-fashioned money, isn't it? 1 pound of water by 1 degree Fahrenheit. I love the way we mix a lot of things up in there, okay? And that calculates a number of kilojoules that are required. Now, what we're really interested in data centers is the BTUs per hour, because we've got to match the way that the speed that temperature builds up in comparison to the speed that we can get rid of that temperature. So your AC system will probably have a rating that tells you how many BTUs per hour it can get rid of, or how many it can cope with. And in contradiction to that, it basically says that our devices will produce so many BTUs. So it's a balancing act. Kadir, yeah, if you need to leave, you've got other commitments. So we've got to balance that act up. So what we have is a heat load calculation check. So the way we do it is we identify the systems in our data rack, and our data rack systems tend to be either rated as a BTU per hour. A lot of systems will actually have, the manufacturer will have a BTU per hour. That's a maximum BTU per hour, because of course we know the more we run a server, the harder we make it work, the more processing it does, the hotter it will get. So it tends to be a maximum. And they also tend to be rated in watts. So we've got two options of how we get that BTU. As I say, first of all, the manufacturer will actually stamp it and tell you what it is. And secondly, you can look at the wattage on the server. So the way we convert watts to BTUs is we basically take the watts and we times it by 3.412. I told you there'd be a bit of maths in today. I apologise for those that do not like the maths. But it's quite easy. It's a simple multiplication. So we take 1 watt, we times it by 3.412 to get essentially 1 BTU per hour. So here's an example here. So we've got 4 servers in a rack. Each server is a 500 watt server. We've got 2 switches at 200 watts. We've got 1 storage device, that is actually rated as BTU per hour. So we can very simply calculate that maths. So the total power consumption for the 4 servers is going to be 500 watts times 4, giving us 200 watts. God, I had to check that maths to make sure it's right. We got a total power consumption for the 2 switches, which is 2 switches at 200 watts, which is 400 watts. Wow, that's great. And 1 storage device, they've already told us the BTUs of that, which is 2000. So to build those servers, we've got 200 watts for the servers times 3.412, giving us a total wattage of 6,824 BTUs per hour. So that's how much heat we can expect those units to provide. So on the flip side of that, we need to make sure our AC can get rid of that many BTUs. Our switches are 400 watts. We times that again by 3.412 and we get 1,364. Look at that, isn't that great maths? And we can add all that up to give us a total for the storage device. the servers and the switches to give us our total heat load, which is our balancing load for the heat of a 10,236 BTUs. That's maths for you. Okay, that wasn't super tricky, and we will be doing a little bit of that. We might want to write down that beautiful number of 1.34, I think it said, wasn't it? No, 3.412. Thank you very much, Patrick. Write it down somewhere because we might be using it later. See, I give you subtle hints and clues about what's going to happen in the future. So we'll have a look at what we call our thermal performance metric. Okay, this is where we talk about how our rating is going to work. So the common metrics that we measure are the rack inlet temperature. So what's the temperature for the rack inlet? When we talk about the inlet, this is our cold aisle. Okay, so that's what we're talking about. The return air temperature is the temperature that comes out, which is basically our hot aisle or combination of the hot aisle. Delta T is the difference between the two temperature. Okay, so a very simple piece of maths there. One minus the other one gives us a difference. And then that gives us a rack cooling index, which is the percentage of racks and cabinets staying within the recommended intake temperature range to give us our overall room compliance. And then we throw one more metric in, which is our airflow. Okay, which is the volume of air circulating through the equipment in the data center. These are important because by continuously monitoring these, we can make tweaks and we can make small changes to systems to allow us to improve our performance. For example, if you have a set of racks that's empty, you don't want to be continuously blowing cold air into those and simply doing nothing with it. Okay, so if we have ones that don't have a very big BTU supply or need, then we don't need to throw shed loads of cold air into those. Cubic feet per minute, yes. CFM, Daniel, thank you very much. There's a TLA basically picked up by Daniel, well done. So we've got a small video that we're going to share with you here. It all, in terms of the ash air, basically the air conditioning guys who have done all the maths for us, and they've worked out what we should and shouldn't be doing and the temperatures we should be working at. Any questions around what that is basically telling us? There's one question I should probably ask is basically what a dry bulb temperature is. Don't know if anyone really cares about that or not cares about that. It's an important measurement. Dry bulb temperature, basically, it's the temperature of a thermometer that is shielded from other heat sources such as radiation, or another light source. So essentially it's a shielded one, so it's not exposed to water vapor or to direct light. Think of it as a thermometer in a dark box. Okay, so let's have a look at the rack temperature. So rack inlet temperature, as we said, this is the temperature at the front, as in normally what we consider to be our cold aisle. It's normally measured in several different locations. Okay, it's measured simply by thermometers is the best way to basically do it. We have these systems that will report back to us, and indeed we can produce pretty schematics and very good pictorial images of essentially how a data center is performing, how each rack is performing. So we could get high inlet temperatures as a result of low cool air volumes, as in our air conditioning is not pumping stuff around enough. Could be circulation issues where the cold air is not able to get out from there and do its job. It's not able to get sucked through, so it stays in that location. High room aisle temperatures are the typical one. As I said, it's normally the cold air, cold aisle section that we put these in. And the traditional solutions are exactly what it says on the tin. So increase the air-cooled flow intake. Could be it's blocked. Could be someone's decided to put a box across the air conditioning intake or outlets rather. And that's causing some issues. We can adjust the containment layout, which is where we talk about our layout for our systems. Is the containment layout correct? Is it making the most of it? Many data centers basically implement a 1 to 2 inlet temperature sensor per rack. So depending on how important it is for you in terms of keeping that temperature correct, yes, imagine that 1 to 2 per rack. Delta T, we spoke about that before. Delta T is the measurement between the intake and the outtake. So essentially what goes in the front, so our air-cooled system, and our hot aisle at the back end. Now this basically ensures that you're using it efficiently. The delta T ratio basically tells you how much of that cold air is being used and heated up and then pumped out the back. So a higher delta allows more heat transfer within the same airflow. So you're not needing to pump more air because you've got a higher ratio there. Typical range is normally 18 to 27 Fahrenheit, which is 10 to 15 degrees C. So that's how much heat we are taking away from the systems. Again, managing the delta T. This is where we talk about our blanking plates. If we don't have our blanking plates in properly, we will get a low delta T ratio because the cold air is able to drift into the warm air and therefore reduces that. So we should make sure we have segmented hot and cold areas. Blanking plates are in, cables are all out of the way, and that's how we tend to improve things. Feel free to spin any questions up as you go through. So let's have a look at some cooling and monitoring activities. Kind of composes of two components. We're going to have a little activity. This is where you guys have to do some work. And I'd like to say I get to have rest, but that's not true, is it? Patrick's asked, higher delta T tends to mean more efficient movement of air. That's right, because you're taking the air from the cold end and you're able to get it heated across the heaters. Think of them as heaters, which are your servers and stuff. So it heats up and therefore you have a higher temperature at the back end. If both temperatures are close, as in if you have the same low cold temperature at the front and the same lower cold temperature at the back, you've not got a decent flow through there because you're not able to pass the air across the hot components that then heats up the back end. Does that make sense, Patrick? Great stuff. Remember, we use the word efficient movement to mean not basically going straight through the system and not warming up. So if it's efficient air movement, it goes across the hot components, heats up, and goes elsewhere. Perfect. Good question, though. Thank you, Patrick. So here we go then. So we're going to have a little activity here. So pick one of the following major data center cooling performance metrics. To research. Return air temperature, supply air temperature, related humidity. Okay, there's 6 of them there. So pick one. We're going to give you, let's give you 5 minutes, okay, to pop away, have a little bit of a research, choose a particular metrics, and these are the questions that we want you to be able to answer. And as you do your research, we're then basically going to have a pop your answers into live chat, and we'll see how messy that gets. Okay, so we'll give you 5 minutes. So that means we're coming back at 6. I was going to say 6:55, but I'm in UK time, so that means nothing to you. In 5 minutes' time, so it's some hour 55. Certainly at this point as an instructor, I hope we've managed to pick different ones and we're not all basically picking the same. I could be lucky this week. Jeffrey's picking dew point temperature. That's good. Stefan's picking the rack cooling index. Yinka's picking the RCI as well. Nima airflow, CFM, well done. As is Melissa. Now, I'm not going to pick on anyone particular, but what I am going to do is we will run through from the top down and we'll have one volunteer to basically paste their stuff up and we'll have a little chat. Okay, last minute, please, then. Okay, so are we ready? You've had a little time to do a bit of a research. Who fancies doing return air temperature? Literally all I'm after you when you volunteer for this is to post in the live chat a definition, the importance, measurement, recommended range, and any troubleshooting. Should have started with one of those that someone picked, shouldn't we? Have I got any takers for doing return air temperature? It's probably one of the boring ones, so. Can't see anything in live chat. Okay, I'll tell you what, let's do it the other way round. Oh, hold on, Daniel's gone. Daniel's pasted something in there that says the rack inlet temperature measures cold air supplied temperature entering the front of IT equipment. Simple and critical to ensure the rack stays within ASHRAE guidelines of 64 to 80 degrees Fahrenheit. Good cut and paste, I like that. Daniel's even jumped in and done the return air temperature as well. Oh, with both. Says the return air temperature measures hot exhaust air temperatures, returning to cooling units, important for setting optimal supply and return air temperatures. Very good. Thank you very much. So who wants to pick relative humidity? Feel free to smash it in. If I get more than one, that's great. I can read a couple out. Relative humidity. I think, Catherine, you picked that. Have you got anything for us, Catherine? You can be shy or you can post it up. Ah, Sunil, thank you very much. There's a bounty of sweets coming your direction for stepping into the breach, as well as Daniel. You got one straight away. So relative humidity, Greg posted it up there as well. Relative humidity is the ratio of how much water vapor is in the air to how much water vapor the air could potentially contain at a given temperature. Boom, yes. RH, Greg basically backs that up by saying RH measures the amount of water vapor present in the air compared to the maximum amount. Catherine's put in the answer for how much should be there, between 30 and 70%. Joshua's added in. Thank you very much, Joshua. The sweets are all going around left, right, and centre here. It's crucial to prevent equipment damage and ensure the optimal performance. Yes. But we do have cooling systems in our system. So if our humidity becomes too much and it hits the system, remember we said things such as this are cold. If it hits something cold, that cools the air and therefore the humidity will form on that device. Catherine says that sensitive parts could make or break something. Joshua's in there. It's critical to prevent equipment damage and ensure optimal performance. Very good. Thank you very much. Okay, let's see. So, Melissa's even throwing things in there. Airflow measures. Oh, airflow's gone in. Airflow measures. Whoa, everyone's got a key now. Everyone wants the suite. Melissa has jumped straight in with airflow. Measures how much air is being delivered to or exhausted from the servers or other IT equipment to remove heat. Yes, so it's a very simple measurement of airflow. Daniel's basically posted a message on there. What does high humidity mean in data centers? How do you troubleshoot that? HVAC, as we said, is heating, ventilation, and air conditioning. We know that your air conditioning systems remove water from the air because it is cooling. So as soon as you cool something, moisture gets formed, and therefore we remove water. You'll tend to find most data centers have a fairly low humidity, essentially. God, there's lots of great ones coming in now. I should have given you all an extra couple of minutes, shouldn't I? So Danielle, to answer that, high humidity. So if your humidity is high, there's a lot of moisture in the air, potentially. It's a bit like being abroad. So you get a lot of moisture in the air. In a data center, that means that moisture will potentially form on cold areas of your data center. In cold areas of the data center, we don't want that to form because it will basically mean you will get liquid on your servers dripping from places, and that's not what we're after. How do you troubleshoot that? Essentially, you look at your air conditioning system or your HVAC system. They tend to be called HVAC systems, where we are conditioning our air. Part of the conditioning of the air is removing the moisture, removing particles, so they go through an air filter, a water filter, to remove all those items that we do not want in there. I remember I asked, it feels like years ago at the start of the lesson, has anyone taken apart a machine that has been sat on the floor, a PC that's been sat on the floor running for a couple of years? In there, you will notice you get lots and lots of dust. You blow in it, the whole thing puffs up in smoke, goes in your face, and is all horrible. Within data centers, they take out all those particulates. They take out all those with the HVAC system to condition the air. And that prevents that happening inside our servers, which means our air cooling systems still run efficiently because they're not covered in dust. I hope that answers that question for you, Melissa. There's a lot of good stuff coming in there. Gabrielle, it's a fantastic one. Gabrielle basically wrote an essay on this. It's really good. Thank you. I will leave you all to read that in your own time, but please do read through Gabrielle's. Dew point transmitters are small, cost-effective, and suitable for a wide range of safe, hazardous environments. Some very good articles coming in there. Joshua's basically put in about hygrometers, which are environmentally monitoring systems, intelligent PDUs. Christopher's, this has gone better than I thought it was going to go. You smashed it, guys. Thank you very much. Christopher has done CFM, stands for cubic feet per minute. Unit for HVAC. What does it measure? Catherine, dehumidifier is basically your HVAC system. So your HVAC system will basically dehumidify things. In data centers, we don't have a separate dehumidifier because it's basically the one-off system that copes with it all. Great stuff. Well, thank you very much for taking part in that. That was really good. I don't think you can sit down and rest yet, because what we've got is we've got a goal 2. Now, I said we'd have to do some maths. Who remembers that magic number I said? We're converting watts. Thank you very much, Daniel. Oh, Bertrand in there. Oh, look, Catherine. Good, good, good. Okay, so pick one or the other of these 2 racks. And I want you to calculate the BTUs. BTUs per hour is what we're after for the maths. As soon as you've got an answer, feel free to smash the workings, small bit of workings, and the final answer into the live chat window. Don't worry about the redundancy at the bottom. We can do that basically if we've got a little bit of time, which we might well have anyway. Sorry, Catherine. Deal with computers, unfortunately. The maths comes out every now and again, doesn't it? But you sat at a computer, it's got to have a calculator on it, isn't it? So we should be okay. Patrick's been straight into school there. Look at that. Rack 1. Look at that. Rack 1 comes out with 12,283.2 BTU hours. Not sure where, Nima, you might need to, for all equipment. Did you do option 2, Nima? Doubling the power consumption, yes. So that's why I said we wouldn't worry about the redundancy system, because I think most of us can times the number by 2, can't we? So let's focus on either doing rack 1 or rack 2. And if you can put which rack you're doing, because Nima's confused me there. Good, I'll give you another couple of minutes if people are still doing the maths. Josh has got a number for rack 2. Stephen first. Stephen beat you, Joshua. My apologies. Very close, though. Barely a second between you, wasn't there? So we've got 8,188 with 2 servers at 400 watts each, which is 800 watts. So 800 watts times our magic number of 3.412 plus 3 switches at 200 watts. So that's 600 watts. And then 2 storage devices at 500 watts each, which is 1,000 watts. Nima R2. Nima, you said R2 on that. I'm not sure your numbers are great there. Oh, hold on. Let me put it a different way, Nima. Either you've got it wrong or Stephen and Joshua have got it wrong. I will totally confess now, I didn't actually calculate rack 2. Oh, Nima's got it here, server. So 2 servers at 800 watts. Perfect, Nima. Fantastic. Has anyone got any questions about how we calculate our BTUs and why we use BTUs then? And what we need to do in terms of balancing our BTUs with what our air conditioning or our HVAC system will cope with. Now, a lot of people may say, oh, it's not that important. Well, it is really important because when we look at the load, when we look at what we actually put into each of our individual racks, in each of our individual aisles, let's imagine our cold aisle, or basically our we've got a cold aisle, we've got 2 sets of racks that go down the left and the right hand side. Each side, so the left side has got 10 racks, the right side's got 10 racks. And we've got 20 of these systems, 20 of these basically replicated across our site. So we can calculate the BTUs, and it's important you look at your BTUs in terms of balancing that. I wouldn't want to put all the hot stuff into one rack and simply blow my air conditioning through the entire building. So if we balance it and we balance the BTUs across the different cold aisles that we've got, we then know we're blowing a balanced amount of cold air into each of those cold aisles. As I say, if I put all of them in, all of the hot stuff in one section, then my air conditioning for that particular section has got to work particularly hard. Not only that, if the air conditioning for that particular section fails, I know that possibly the backup air conditioning unit on that may not be as powerful and therefore may have problems maintaining the temperature that I need. Great. Well, I really enjoyed that. I know some people hate the maths, but thank you very much for sticking with it. Some really good answers. Thank you. So as I say, it's important to balance the racks and make sure you know where your BTUs are so that you can then balance everything out. So last but not least section, thank you very much, is troubleshooting. These are, again, our basic troubleshootings. We know we do a lot of this stuff, and we spoke about it when we did the power. A lot of it is about preventative maintenance. Scheduling our regular checks. Well, what we're doing for regular checks, we're looking that things are clean, sensors are calibrated properly, fluids and filters are good, replacing any particular filters that we need. If our HVAC has got an AC system, as in it is doing an air filter, yes, we need to regularly replace that air filter, just like you would on your car. You'd replace the air filter every now and again. Cleaning, yes. If we've got things such as general maintenance, such as boxes and things like that being placed across grids in our cold aisle, that is stopping the effectiveness of it. We can check when we walk through our aisles as we're casually walking through, whether or not all the plates are in place that need to be in there, the blanking plates. And really with it, we should also have some automatic triggers, alerts for pending maintenances. So it needs to be on a schedule, on a rota. Monthly inspections is what's basically done in terms of visual inspection for sensors and equipment. We said about checking sensors. Yes, we know we've got temperature gauges on the front and the back of our systems measuring the temperatures. Are those temperature sensors working? Are they correct? So we need to take a calibrated temperature sensor, stick it next to the one that's measuring it and go, yes, that is correct. Because if that's faulty and it's giving false readings, we're blowing different air around the wrong place. So monthly inspections are good. Make sure you've got good SLAs, service responses. Remember, if your HVAC system falls over, who's going to fix it? Do you have an agreement with a particular company that says we're going to come in X number of days, X number of weeks, X number of hours to fix it? And we've got to remember that essentially our backup system or another HVAC system should be able to pick it up and cope with the load, which is why it's important to balance our BTUs around our estate. Do you have a list of qualified technicians on site that are capable of dealing with the initial faults, the initial troubleshooting? Again, this is all about training properly, making sure you have the right trained people and the right people on shift. No point having a shift where you don't have someone who's got HVAC experience on, because that'll be the day that the HVAC falls over. And you need, just like you do with your boiler and your air conditioning system for you people, budget for an annual tune-up. Because we know there are going to be leaks. You do lose some cooling fluids, the water basically needs changing and things like that. So we need to budget for those annual tune-ups that will keep the system running efficiently. Anyone got any questions about that particular part of the general troubleshooting and safety? Give me a second to type something. I'll try to fix it. Make my copy. There are other tools that we can use. There are things such as the thermal imaging. Yeah, why don't we use thermal imaging? Yes, it's great. So we can use thermal imaging in our data centers to wander around and look for hot spots, look for cold spots, look for where things aren't working properly. Ideally, we want to see a nice, clean, regular flow. We want to see things that are nice and even. If we get our thermal imaging camera out and we find spots in there that are like red hot, ask ourselves, why are they red hot? Should they be red hot? Okay, should we see things such as this, where we've got a hot face? If we see that sort of image on a server, then we know there's something on the server that is heating up. Should it be heating up? Is it simply a case that that is an image of our processor and our cooling fans on there that essentially we expect to be warm? Or is it a case that something such as our power supply unit is warming up too much? If this one is hotter than the other one I've got in the system, why is this one working harder? Is this one about to go? And we can check that with our regular maintenance. So anyone, thumbs up if anyone's used a thermal imaging camera, and what have you used it for? I used one once. I'll tell you my story first. I used mine once to check the insulation in my loft. I put some new insulation up. I put some thermal barriers in, trying to increase the energy rating of my property. Went outside with a thermal imaging camera to check things. Yeah, it looks good. There's some hot patches that I then knew there was a hot patch. So I then knew I needed to apply more insulation at that location. Nemo's used it in a security job. What is that? Is that to find people? Find people that are hiding? God, wasn't there? I think there was it's wrong. There was a spate of YouTubers that were basically trying to spend weekends in department stores and things like that. They'd lock themselves or hide themselves around. Not a camera, but a scope. I do. Oh, regularly in a hog hunt. I take it that's shooting wild boars and pigs and things like that, is it? Living in Walmart and such. Yeah, what a dream job. Wow, that's very interesting, Joshua. Remind me to try and get an invite to your next barbecue, Joshua, if you do hunt a wild boar. I do love wild boar. Sorry, I shouldn't really say that. Okay, so safety. We focus an awful lot on electrical safety. Yes, our HVAC systems are driven by electricity. So there is going to be the traditional electrical safety regulations. A lot of this we cope with training. Yes, training. NOC staff need to receive training. They need to receive not so much certifications, but ticks in the boxes that says they have done the training for this. They are aware of any hazards that may come from HVAC systems, and they are aware of how they need to maintain the HVAC system. They also need to know about emergency responses. So in the event of an issue with a HVAC or a cooling system, what do they do? And these are all basically falls back down into the processes that you'll be given. So as a quick review to the section, we have performance metrics that include vendor contract dates for cooling equipment. We also know there's types of issues that thermal scanning can help detect. So not just using our little thermometers, we can use thermal scanning to basically select and detect any particular issues with our HVAC system. So really, as a conclusion, we've had a good chat already about HVAC systems. We've spoken about cooling methods. We know the difference between the chilled water, the pumped refrigerants. We know the difference between the chilled water air-cooled versus water-cooled chillers. And we know that we're no longer using CFCs or HCFCs, but we're using HFCs for our refrigerant coolant systems. We know how really important it is to have a cold aisle and a hot aisle and to separate the air from each other and make sure that it flows through our servers as efficiently as possible. And we know we can do some beautiful maths for our thermal performance metrics in terms of rack temperature, the delta T's to see how well we're doing. And we can use that intelligently to then make tweaks and make changes to how our HVAC system is performing and what we are doing in our racks. And we had a good little chat about some troubleshooting, maintenance theories, and some safety protocols. That kind of brings us towards the end of the lecture. Has anyone got any questions they'd like to pose or anything else? Before we hand you back for